This is Group 16's Cragside project documentary video. The definition of BIM is Building Information Modeling, and it is an intelligent 3D model-based process that provides architecture, engineering, and construction professionals the insight and tools to more effectively plan, design, construct, and manage buildings and infrastructure. BIM focuses on 5 main elements: processes, policies, people, information, technologies, and it combines all of these elements into one clear system to involve each party through each stage of the project.
Right, so this is the section on the collaborative working within the integrated architecture, engineering and construction practices, also known as the AEC. So basically between all the three disciplines there is a common data environment, also known as CDE. Basically there's 4 stages to this, and it allows all the information of the project to be shared within the members of the team. The first stage is the work in progress. This is the non-verified data. The second is the shared area. It's verified data that's been obviously checked by somebody. There's the published and issued data, which is the validated output for the whole use of the whole team, which has been checked by everyone, and that's the complete design. And then there's the archive, where everything gets stored at the end. So going into them in more detail, the work in progress is developed in isolation by maybe 1 or 2 members of the project. It contains the information that is responsibility of the person who's doing it, the stakeholder, and it is stored in the team's work in progress section in their system. Then it goes on to the shared area. Each party needs to make their data available through an exchange protocol. It needs to be accessible by all from a central location or in the shared area folder before it is shared. But before it is shared, it needs to be checked in line with the BS 1192 workflow. The sharing of models can be carried out if the disciplines are working to the latest validation information. All model files are to be issued with a verified text document to minimize the risk of errors in communication within the project, so everyone knows what's going on the sheets. The changes to the shared area to be communicated through the whole team through meetings or traditional drawing issues or just a simple email. Then it goes on to be published. This is the exported data in 2D electronic drawings. They will be stored in the publication area once formally checked with the BS-PAS 1192 requirements. The record should be maintained in soft copy and hard copy where appropriate, just so that it doesn't get lost. It shall be treated as a work in progress or shared as an uncontrolled document. And then finally go on to the archive. This is the approved output data stored in the archive area. This has all got the published areas and the as-built drawings and data. At the key stages of the design process, complete versions of the model, exported data and associated drawing deliverables are copied into the archive area, and the data shall stay there in the folder that clearly identifies the stage of the design that it's at, so there's no confusion about whether it's finished or not. Preparation for publishing, basically the structure and context need to be approved by multiple members, just to make sure it's up to date and it's valid. And when it has been approved, then the sheets need to be published as a PDF, WF, or another non-editable format so that no one could change any details. Overall, within this legislation within BIM, it helps all members of the AEC community to basically trust each other, because they can visualize all the work better. It allows all the members to work together and input ideas onto the project instead of just one person doing it or a few people. It allows use of many input resources that can be converted into one format. And the major reason for it being so good is that it increases the cost and time efficiency of the project drastically, just because multiple people can work from different areas at the same time on the same project instead of the old-fashioned way of just one person doing it at a time and passing it on through paper.
Advanced project monitoring tools in detection and prevention in AEC projects.
What is a clash? A clash describes an inconsistency in the design of a building or in the sequencing of building works. There are three main clash types: hard, soft, and schedule-based. A hard clash occurs when two separate building elements take up the same space, whereas a soft clash describes a lack of space left for another element to fit into. For example, pipework running through areas already taken up by beams is a hard clash. Tolerances left too small for mechanical units to be maintained correctly are soft clashes. Schedule-based clashes are caused by poor illogical project planning. For example, wagons arriving during the construction of a temporary hard standing, and the hard standing is incomplete so the wagons can't get onto site. Clashes can cost the principal contractor time and money. Too often, clashes are discovered on site during construction works. They require rectification, which may involve the editing or removal of building elements constructed prior to detection. Therefore, clashes often result in added material costs, delays, or even penalties. They can also cause serious injury on site if an unexpected clash causes a collapse. Scheduling clashes also result in delays and can greatly influence the relationship between principal contractor and subcontractors. If a subcontractor arrives on site and they aren't required to work yet due to a scheduling clash, the subcontractor may choose to not do any work for the principal contractor again. Worse, it may breach a contract and result in penalties for the principal contractor. Clearly, clashes have a huge impact on the success of a project. Successful projects should aim to detect as many clashes as possible prior to the commencing of site work. On a building project, design teams from each discipline produce drawings on building elements that they are responsible for. Prior to BIM, coordination meetings occurred, but most work was done in isolation, without sufficient knowledge of the design that other disciplines had in mind. This type of working environment discourages collaboration between separate disciplines. During meetings, the 2D drawings are checked for compatibility by overlaying them on a light box. Obviously, this makes clashes difficult to detect. Scheduled clashes could only be detected by another planner looking at the planned program. Now, BIM links the design of each building element, the construction program, and the project's 3D model. This ensures compatibility between designs created by all construction disciplines involved in the project. With all the above data inputted into BIM software, it is easier than ever before to detect clashes at a pre-construction stage. This potentially cuts costs massively and minimizes delays. The clash detection software can even be manipulated to ensure building regulations are met. Clash detection in BIM. Navisworks is an example of BIM software which provides clash detection technology. An algorithm called Clash Detective allows the user to select any two elements of a building, for example, pipework and fire protection. The tool allows the user to search for hard or soft clashes in the 3D model. Tolerances can also be entered to allow for any inaccuracies encountered when installing elements on site. If the tolerance is set to 5 mm when searching for a hard clash, only objects overlapping by more than 5 mm will be shown. When searching for a soft clash, or a clearance clash as the program refers to it, any objects within 5 mm will appear as a clash. When the algorithm is run, the clashes will all appear highlighted in the 3D model. This is shown below in the image, which demonstrates how easy BIM makes it to detect and visualize clashes in the project. Despite this, there are still challenges involved in using BIM for error detection. These mainly stem from human error when using the software. For example, inputting the wrong dimensions for a beam may show there are no clashes present, and the clash will be detected later on site. Despite this, the use of one shared model reduces the chance of an error like this going unnoticed, as everyone can see the model and call up any errors at any time. As the usage of BIM in the construction industry becomes more common, attitudes will change as engineers accept it as part of their role, causing these challenges to decrease significantly.
Advanced decision support and project information management tools in AEC practices. Information regarding the processes. Advanced decision support and project information management tools are used during different construction phases. There are many examples of different tools that all have their own individual usefulness when using them on site. Some examples of these include GIS BIM. A geographic information system is an information system that captures, stores, manages and presents geographic data and The integrating of these two together in 2017 was a revolutionary for design construction management. By linking them, it allowed the designer to design in the context of the site's geographic information. Augmented reality. Before the project is executed, AR provides the teams with a walkthrough of the entire project, including its details and exact measurements. Architects, the project manager, and engineers get sufficient data that ensures both accuracy and speed as well. AR also gives them a chance to navigate each project phase and see if any errors before they surface later. Other benefits include you save money and time, the accuracy of the construction projects goes up because everyone can see all the details that are linked to it. Actual construction of the building, because augmented reality accelerates construction process because team members can have quick and instant access to virtual models, so they don't have to look on site, it can just be done in their own time. Photogrammetry. Photogrammetry is a form of 3D scanning that uses photographs and triangulation to create an accurate model of a site or structure. Photogrammetry scanning can be performed at close range via satellite or from the air. For construction projects, drones have transformed photogrammetry for an expensive and time-consuming operation to a simple and inexpensive one. During construction, it can be used to monitor progress and analyse any problems that arise as they occur. Record modelling. This record BIM will describe what has actually been built with geometrics and specifications parameters wherever appropriate and as far as that is practical, and assembly drawings showing actual dimension details rather than those in contractual construction BIM. For Cragside design projects, these tools were used to make sure the scheduling of resources was done in an efficient way with as little time wasted as possible. The disadvantages of using the process on site. There are disadvantages using these processes on site, such as the obvious ones of time and cost, but there are other ones such as information overload. A computerized decision-making systems may sometimes result in information overload. Since it analyzes all aspects of a problem, it leaves a user in a dilemma of what to consider and what not to consider. For people on work site, it's confusing whether to know, when you give them such high level like schematic stuff, where the problem lies and stuff. Overemphasis and decision making. Clearly the focus of computerized decision making is on considering all aspects of a problem of all of that time, which may not be required in many of the situations. Cost of development. The cost of decision making decreases once decision support system is installed, but development information of a DSS requires a huge monetary investment, which for some construction sites may not be a possible option. Training. Not every person on site has the ability to understand every photo shown to them if it's too advanced for them, therefore training may be required for certain sites when these drawings are used.
Potentials and barriers of adopting digital engineering BIM integrated project delivery within AEC domain. Pre-construction. The owner will be able to see all the materials being used for the building, so they can see if it meets their financial requirements. They will also be able to see if the building meets all the requirements that it's built for. BIM allows the option of overlapping work as well. This means that the building will take less time to construct and will be much cheaper. Construction. Quick automatic changes to the construction work. If something in the design needs to be changed, this will affect the rest of the construction, but it won't matter as all of this will be automatically changed to fit in. BIM will show any errors in the construction phase. Therefore, if the dates don't match, it'll pop up telling you this so it can be changed. It also shows any potential hazards. This leads to safer construction as any precautions can be made. Post-construction. It's much easier commissioning and handover of the building, as the owner will quickly know all the systems used into the building and how to operate them quicker. You can check if all the buildings are in order and working correctly due to BIM, and you can see if any maintenance is needed. Any improvements will be more efficient as well, as the design model will still be around and you can just add to it or take away from it. The current barriers of BIM are some data could be missed out due to human error, legal issues as who pays for the design, model and the analysis, the owner or the construction worker, and not many people will know how to use BIM as it's fairly new and they'll have to learn it from scratch, meaning that the first few times might not be as good as the rest.
As shown during the PowerPoint, it is clear that BIM is a very useful tool which is used throughout the whole project. It enables all departments a visual representation of the project, therefore can provide suggestions and improvements along the way. Also, it allows all parties to communicate together to ensure the project is completed professionally. Moreover, as the technology advances, BIM will also improve at a steady rate.